Section 1. Introduction. Let's delve into the question. Can language models recognize when they're producing information that isn't based on reality? This is a question of whether they can detect when they're hallucinating. The common approach to this problem is to treat it as a text entailment issue. Most of the previous research has focused on developing secondary detection models that are trained on and applied to the surface text. However, these secondary models are often as complex as the original language model that produced the error, and they overlook the information that was already calculated during the generation process. In our study, we investigate how well probes on a decoder-only transformer language models feed-forward and self-attention states can detect hallucinations in various grounded generation tasks. Specifically, as the language model generates a response, we examine its encoded tokens to see if the model has just started to hallucinate or will eventually be found to have hallucinated. It's possible that these encodings are aware of whether the generation is retrieving information that is based on the prompt or just filling in plausible information that is stored in the model's weights. We've designed 3 probes of increasing complexity across 3 grounded generation tasks: abstractive summarization, knowledge-grounded dialogue generation, and data-to-text. For each task, we gather hallucinations in 2 ways. 1. From sampled responses, where we generate outputs from a large language model, LLM, based on the inputs, or 2. By editing reference inputs or outputs to create discrepancies. We refer to these as organic and synthetic data, respectively. In both cases, we have human annotators mark hallucinations in the outputs. The second method produces hallucination annotations at a higher rate, but we find that these synthetic examples are less useful as they do not come from the test distribution. Our contributions can be summarized as follows. We've created a high-quality dataset of over 15,000 utterances with hallucination annotations for organic and synthetic output texts across 3 grounded generation tasks. We've proposed 3 probe architectures for detecting hallucinations and demonstrated improvements over multiple contemporary baselines in hallucination detection. We've analyzed how probe accuracy is affected by annotation type, synthetic, organic, hallucination type, extrinsic, intrinsic, model size, and which part of the encoding is probed. We've centered our study of hallucinations in the context of in-context generation where grounding knowledge sources are provided within the prompt itself. This is different from settings where a language model is expected to generate a response entirely from its world knowledge, i.e., grounded in the model's training data. Hallucinations are not necessarily factually incorrect. They can be classified as intrinsic, where generated responses directly contradict the knowledge sources, or extrinsic, where generated responses are neither entailed nor contradicted by the sources. For instance, consider the following task prompt for abstractive summarization. Deckard is now able to buy his wife Iran an authentic Nubian goat from Animal Row in Los Angeles with his commission. A generated summary sentence of Deckard can now purchase an animal for his wife is faithful. Deckard can purchase a goat in Iran is an intrinsic hallucination, and sheep are usually cuter and fluffier than goats is an extrinsic hallucination. Automated diagnosis of hallucinations is a challenging task. Lexical metrics commonly used in the evaluation of natural language generation, NLG, often fail to correlate with human judgments of faithfulness. More useful are natural language inference, NLI, approaches that either directly measure the degree of entailment between a generated response and a given source text, or else break down texts into single-sentence claims that are easily verifiable. These have been successfully used for hallucination detection. Similarly, approaches that leverage question-answer models to test if claims made by a response can be supported by the source text, and vice versa, try to more explicitly identify the grounding sources of given generations in this task. Section Summary. In this section, the authors investigate whether language models can detect when they are generating hallucinations. They propose 3 probe architectures to detect hallucinations in grounded generation tasks and demonstrate improvements over existing baselines. They also analyze how probe accuracy is affected by different factors such as annotation type, hallucination type, model size, and the part of the encoding that is probed. Section. Predicting transformer behavior. We're going to delve into the behavior of transformer language models, specifically how they learn and recall information. In smaller models, we can often pinpoint specific layers and modules responsible for certain behaviors, such as in-context learning. However, this becomes more challenging with larger models. We've found that the feed-forward modules in these larger models act like storage units for factual associations. We can even tweak the weights in these modules to alter the facts linked to certain entities. To test this, we need to check if the recalled facts are used correctly, according to the rules of grounding. This means the facts should be used to rephrase the information given in the prompt, not to replace it or add probable details. Our research expands on this by showing that the hidden states during generation contain information about the recall of facts related to grounding data. However, we found that our annotation taxonomy might not have been detailed enough to let us determine exactly what facts were recalled. We propose a change. We suggest that feed-forward outputs contain signals about how information is recalled from the prompt, as well as claims recalled from the training data. We've also found that the internal states of the transformer can predict the likelihood of a model correctly answering a question in a closed-book QA setting, and in predicting the truthfulness of a statement. However, these internal representations of truthfulness can sometimes conflict with measures of model confidence. We've discovered separate computational processes in transformer language models dedicated to recalling associations from memory versus grounding data. We've also shown that we can detect whether associations from grounding data are used correctly across several distinct generation tasks. We've trained a probe to detect whether a question can be answered given a passage, which is similar to our task and section. However, we also detect token-level hallucination during answer generation, which could occur even in theoretically answerable questions. We've tested hallucination probes for autoregressive grounded generation in 3 distinct tasks: abstractive summarization, knowledge-grounded dialogue generation, and data-to-text. We've used the same high-level prompt structure across all tasks to generate model responses and to probe for hallucination. We've used the Llama 2-13B model to generate outputs for each task. To ensure a good mix of both hallucinations and grounded responses in the generations for each task, each model response is generated using top K random sampling with K equals 2. The number of few-shot in-context learning examples for each task was chosen through a pilot exploration of several generation strategies. We aimed for a good balance of hallucinations and grounded responses in all tasks, as determined by manual inspection. For automatic summarization, we used the CNN Daily Mail dataset, a standard benchmark. We prompted our model to generate abstractive summaries of news articles by appending TLDR after the article content and taking the first 3 generated sentences as the summary. For knowledge-grounded dialogue generation, we used a given conversation history and a provided knowledge sentence obtained via Wizard of Wikipedia. The task asks a respondent to create a next-turn response to the conversation that is grounded in the provided knowledge sentence. Here, we prompted our response model to generate grounded responses under 2-shot in context learning with example grounded responses. Section Summary. In this section, the authors discuss the behavior of transformers in language models. They provide evidence that the feed-forward modules in larger language models function as key value stores of factual associations and can be modified to edit facts associated with entities. The authors also mention the use of probes to determine whether recalled facts are deployed in accordance with the rules of grounding. Section: Data-to-text generation. We're going to talk about 2 main topics: data-to-text generation and synthetic hallucinations. In the first part, we're dealing with a task called E2E, which involves writing descriptions of restaurants based on given attributes. We trained our model to do this task using a method called 10-shot in context learning. However, the original E2E task had some missing information in about 40% of its data, so we used a cleaned-up version. Even then, there were still some instances of missing information, so we manually selected and verified 10 examples to ensure they were accurate. Now, let's move on to synthetic hallucinations. Recent studies have created synthetic datasets by hand to test metrics for measuring unfaithfulness and models for detecting it. The BUMP dataset is a version of CDM where the reference summaries have been manually edited to be ungrounded. It includes both freestyle edits and systematic coverage of 4 specific types of faithfulness errors: predicate errors, entity errors, circumstance errors, and CO reference errors. We used BUMP in our CDM experiments. For our Conva Fever and E2E experiments, we created faithfulness errors in a uniformly sampled subset of these datasets. We changed the provided knowledge sentence so that the existing reference response would be unfaithful to it. This simulates the common case of hallucination where a large language model generates statements that may be true, but which are not grounded in the source documents as required. For Conva Fever, we prompted ChatGPT to modify a given example's provided knowledge sentence to introduce intrinsic and extrinsic errors of types 1, 4, above. We then manually judged these attempts and edited the unsuccessful ones. This process proved to be inefficient as it required significant human editing and validation. We created equal numbers of examples with intrinsic and extrinsic predicate, entity, circumstance, and CO reference errors, as well as freestyle errors. For E2E, we modified a random subset of the provided grounding attributes. We then manually verified that the reference response was unfaithful with respect to the modified attributes. If not, we further edited the attributes. Next, we asked annotators to label the minimal hallucinatory spans in each response, if any. These are the smallest text spans that would need to be modified to transform an ungrounded response into a grounded one. A team of 17 annotators completed a pilot annotation exercise of 50 annotations per task. These pilot annotations were checked and verified by the authors to pinpoint common sources of error and disagreement. This feedback was integrated into a revised set of annotation guidelines, and the full dataset was then re-annotated by the same team. Each example was annotated once. Note that for each dataset, over 1/5 of all annotated responses were annotated as containing at least one hallucinated span. Finally, we used probes to analyze a neural network's internal representations. These probes, often taking the form of linear classifiers, are applied to the internal representations of a network and are trained to discriminate between different types of inputs or outputs. We are interested in detecting hallucinatory outputs during a language model's generation steps when conditioned on a prompt that requires a response grounded in the prompt. To determine whether a response to a prompt contains hallucinations, we will probe the hidden states of the transformer language model as it generates the response. These hidden states depend on the prompt and on the prefix of the response that has been generated so far. They can be reconstructed from the string pair, prompt, response, via force decoding. A single transformer layer actually consists of two sublayers. The first transforms a token's embedding by adding a vector predicted by attention, and the second transforms it again by adding a vector predicted by a feed-forward network. We train a separate probe for each of the two L sublayers, where L is the number of layers. Section Summary. In the data-to-text generation task, we use a cleaned version of the E2E dataset and manually select and verify 10 in-context examples to ensure groundedness. We also create synthetic ungrounded datasets, such as the bump dataset, to evaluate unfaithfulness metrics and detect ungrounded statements. To analyze the neural network's internal representations and detect hallucinatory outputs, we design probes that examine the hidden states of the transformer language model during generation steps. Section. Linear probe. We're going to discuss 3 different types of probes we used in our study: linear probe, attention pooling probe, and ensemble probe. First, let's talk about the linear probe. This is a linear classifier that uses a single hidden state vector as input. In simpler terms, it takes the output from a sublayer of our model and uses it to make predictions. We denote the response token as x_i, and the corresponding hidden state as h_i. We use y_i to indicate whether x_i falls within a minimum hallucination span. The linear probe predicts y_i using a sigmoid function applied to the sum of the product of a weight vector w and h_i and a bias term b. We also considered a version where h_i is replaced by h_i1, as it is h_i1 that helps generate x_i and decides whether to hallucinate it. We hypothesize that h_i1 performs better at higher layers while h_i performs better at lower layers. Next, we have the attention pooling probe. This probe takes into account previous hidden states of the response. It uses an attention mechanism to pool over all hidden states so far. The attention weights, denoted as alpha_i_j, are computed using a learned query vector Q. Our final approach is the ensemble probe. This is a single feed-forward layer that combines the predictions from our 2 separately trained probes. The individual probes are frozen before the parameters of the ensemble probe are fit. We also trained a classifier to predict whether a response contains any hallucinations at all. For this, we used an attention pooling probe over the entire response. In terms of evaluation, we used F1 score, which is the harmonic mean of recall and precision. For token-level classifiers, we evaluated the F1 score of their per-token predictions. However, we were more interested in span-level F1, which considers whether we predicted all of the annotated hallucinations and whether all of the predicted spans were annotated as actual hallucinations. We modified span-level precision and recall metrics to give partial credit. We defined a span as a set of tokens, and computed the recall as the average coverage of each reference span, i.e., the fraction of its tokens that are in some predicted span. Similarly, we computed the precision as the average coverage of each predicted span. We then defined F1s_P as the harmonic mean of precision and recall. Section Summary. The linear probe is a classifier that uses a single hidden state vector as input to predict whether a response token falls within a minimum hallucination span. The attention pooling probe considers previous hidden states of the response as well and uses an attention mechanism to make predictions. The ensemble probe combines the predictions from the linear and attention pooling probes. Additionally, there are token-level and response-level classifiers that evaluate the F1 score of their predictions, with the response-level classifier focusing on span-level precision and recall metrics. Section 5 Experiments. Let's delve into the experiments we conducted. Unless we specify otherwise, all our evaluations were carried out using real-world data, even if the tools we used for testing were trained on synthetic data. We started by training single-layer hidden state probes, as described earlier, using float32 precision and unregulated log loss. We used a batch size of 100 and atom optimization with a learning rate of 0.001. The parameters beta_1 and beta_2 were set to 0.9 and 0.999 respectively, after conducting a small grid search on hyperparameters. We divided our data into 70% for training, 10% for validation, and 20% for testing. Each classifier was trained using early stopping with a patience of 10 epochs. We then trained an ensemble classifier using the predictions of these single-layer probes as input, with the same hyperparameters. We compared our probe's performance against a range of current methods used in faithfulness evaluation, measuring the F1 score for hallucination classification on the test set. These methods included the model uncertainty-based metric of length normalized sequence log probability, off-the-shelf synthetically trained sentence-level claim classification, linguistic feature-based dependency arc entailment, QA-based metrics, the NLI-based metric, and ChatGPT classifiers with and without chain-of-thought prompting. These metrics were not originally designed to detect hallucinations in individual responses, but rather to evaluate a collection of responses for system comparisons. However, we adapted them to our setting by classifying individual responses based on a threshold set to maximize the F1 score on the validation set. For baselines optimized at the sentence level, we performed response-level evaluation by logically combining sentence-level baseline predictions. We also reported the performance achieved by randomly predicting a hallucination label with a probability tuned to maximize the F1 score on the validation set, which we refer to as optimized coin, OC. On 2 datasets, we were able to match the agreement rate between human annotators. On these datasets, the probes trained on real-world hallucinations performed the best. The exception was one dataset where the real-world probes were slightly outperformed by the synthetic probes, which in turn fell well short of human performance. On all datasets, we were able to outperform all baseline systems, showing that probing is a viable and efficient alternative to evaluating language model outputs when model states are available. We found that our ensemble attention pooling probe nearly met the human agreement rate for one dataset but lagged behind for others. However, even this level of performance could be useful for avoiding hallucinations. When evaluating the performance of trained single-layer probes, we found that signals of hallucination were strongest in the middle layers of the model during decoding. The performance of the probes consistently and gradually increased from the first layer up to layers 10 to 20, after which there was a consistent decline in hallucination classification performance for the subsequent layers. We also noticed slight variations in grounding saliency among different types of hidden states during decoding. Feed-forward probes reached peak performance at slightly deeper layers than their attention head-out projection probe counterparts and exceeded them in single-layer hallucination detection. When we trained ensemble classifiers on only the hidden states of the same type at every layer, we found that feed-forward hidden states had a slightly but statistically significant greater saliency of model grounding behavior. Section Summary. In the experiments section, the authors trained single-layer hidden-state probes using float-32 precision and unregularized log loss. They used a batch size of 100, atom optimization with a learning rate of 0.001, and a train validation test split of the 20th of October 70%. The ensemble classifier was trained using the predictions of these probes as input. The performance of the probes was compared against various baselines, and the probing-based approaches outperformed all baseline systems. The authors also found that signals of hallucination were strongest in the middle layers of the model during decoding, and feed-forward hidden states showed slightly greater saliency in model grounding behavior compared to attention head-out projection probe counterparts. Section. Model size. In our study, we trained probes on the force-decoded hidden states of responses from our dataset using two models, Llama 2-7b and Llama 2-70b. We found no significant difference in hallucination detection across the hidden states from these models of different sizes. This suggests that even when a hallucination is generated from a different model, we can still detect it. Moreover, even the lower dimensional hidden states of the 7b model contain enough information to train a successful probe. Next, we examined the prominence of different types of hallucination behavior in the internal states of the model. We categorized test set responses into those containing intrinsic or extrinsic hallucinations and evaluated the performance of the trained probe in detecting the presence of hallucinations for each type. We found that extrinsic hallucination behavior is more noticeable in the hidden states of shallower layers for both organic and synthetic hallucinations, with the most noticeable peak around layers 15 and 16, and decreasing in deeper layers. Overall, extrinsic hallucination was more noticeable in model hidden states than intrinsic hallucination. We also found that probes are very effective in detecting synthetically created hallucinations across all tasks. However, the performance of the probes drops significantly when trained and tested on different modalities. Probes generally perform better when trained on organic hallucinations and tested on synthetic ungrounded responses, and vice versa, with the notable exception being abstractive summarization on the CDM dataset. Our results also show that synthetic data generation approaches specifically designed for factuality evaluation do not align with actual errors made by generation models in their lexical error distributions. This extends to their hidden state signals as well, which are used by the probe to detect unfaithfulness in the case of force decoding on human-created content, relative to organic instances of hallucination. To test whether the prominence of grounding behavior persists consistently in similar hidden state locations across different tasks, we trained our probe on each specific task and evaluated its performance when applied to the others. We found a lack of generalization in hallucination detection performance for our probes across different train and test tasks. This could mean that there is not a consistent signal of hallucination across tasks, or that our probes are not distinguishing this signal from its task or dataset-specific confounds, and are overfitting to the confounds. In conclusion, our work is motivated by the need for efficient LLM hallucination evaluation. However, one of the key limitations of probing is the need for labeled-in domain data for probe training. Our results suggest poor generalization to out-of-domain tasks, although this might be mitigated by larger and more diverse training sets. Furthermore, probing requires access to the hidden states themselves. If LLMs continue to move behind closed-source APIs, such hidden state probes will not be possible for those without privileged access. Synthetic hallucinations are generally not suitable for organic hallucination detection. These differences in internal representations further suggest that language model behavior during hallucination fundamentally misaligns with current expectations of ungrounded generations. Training on the same modality, synthetic or organic, is crucial to maximize hallucination detection performance, and our results on the synthetic modality, especially on CNN, Daily Mail, suggest probing to be a feasible method for complex multi-sentence entailment classification that can leverage the capability of LLMs. Section Summary. The study explores the detection of hallucinatory behavior in language models, LLMs, by training probes on hidden states. The results indicate that even lower dimensional hidden states contain enough information to successfully train a probe, and extrinsic hallucination behavior is more salient in shallower layers of the model. However, probe performance drops significantly when trained and tested on different modalities, suggesting a lack of generalization in hallucination detection across tasks. Section. Annotator disagreements. We've noticed that there's a significant amount of disagreement among annotators when it comes to identifying the smallest parts of a response that are hallucinations. This is a problem that we're still trying to solve. When it comes to designing probes, even if we could standardize the boundaries of these hallucinations, they might not match up perfectly with the signals of hallucination in the internal representations of language learning models, LLMs. For example, a response might start contradicting a source of knowledge at a certain point, but the signs that it's going to hallucinate might already be noticeable in the parts that came before it. Or, the signal might only be calculated later on, when the decoder is processing the tokens that have already been generated and realizes that it's following a train of thought that isn't based in reality. This suggests that there might be ways to design probes that could do a better job of detecting and mitigating hallucinations. We should also consider using nonlinear probes like feed-forward networks, as their hidden layers could learn to identify different kinds of hallucinations. Once we're able to detect when a response is not grounded in reality, we can start learning how to avoid this. This is particularly important as more and more consumer-facing applications are starting to use generation that's based on retrieval. We're planning to explore this topic in future work. One simple way to handle this is to reject a response or a prefix where we've detected a high probability of hallucination, and then start generating the response again. Another strategy could be to use the predicted probabilities of hallucination to adjust or filter hypotheses during the beam search process. Lastly, we could use a detector as a way to fine-tune the language model by using a reward-based method like proximal policy optimization, PPO. In addition to learning from negative rewards at the response level that are given at the end of the utterance, PPO can also benefit from negative rewards at the token level that are given earlier on. These serve as a more informative signal for reinforcement learning, also known as reward shaping, and can help reduce the complexity of the samples.